I think what I wanted to do in this, with my involvement in this collaboration is try to bridge an approach to thinking about flat space holography, an ab initio theory of scattering amplitudes in flat space that my collaborators and I have been pursuing for 10 or 15 years, where the essential novelty appears to be that if you go to the boundary of flat space, there's nothing super obvious to do there. If you think about the data that labels a scattering process, a bunch of momentum particles and maybe helicities in and out, that's your canvas, that's the space, one way or the other, however you want to think about it, either directly that way, geometrically on the celestial sphere, however we do it, there is a canvas, which is just the kinematic space that labels a scattering process. And this seems to be an austere, almost empty space with nothing going on. It's not like the boundary of ADS, where there's a notion of time, metric, locality, blah, 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 that once you get into the holographic mindset, it's obvious what to do. Here, it's not obvious what to do when you get out to the boundary and think about your canvas, which is the kinematic space. And what my friends and I have been exploring for the past 10 or 15 years is that there are some hidden but quite remarkable, very simple but kind of abstract combinatorial geometric structures that live in kinematic space that allow you to ask questions whose answers end up giving you scattering amplitudes with all their richness and complexity, with all the physical properties like locality and space-time and unitarity, an output, not an input, into these, from these very, very simple ideas. This started with the story of positivity and Grassmannians and the amplituhedra for gluon scattering amplitudes in N equals 4 super Yang-Mills, and in the past year and a half, 2 years, very different setting of a picture of amplitudes in terms of curves on surfaces, counting problems associated with curves on surfaces. I'm not going to review these things. I'm going to use a little bit of it. I'll just use some formulas for the purpose of the talk. But the point is that in these two settings, there's just slightly different ways of thinking about the kinematic space. You either think about kinematic space as n momenta for the scattering particles, or you think about it in terms of the dot products, the Mandelstam invariants between pairs of particles. That's it. That's the only difference. And quite remarkably, in these very austere-seeming spaces, there's just enough mathematical structure to ask questions that spit out, at all loop orders, scattering amplitudes. Now, what I want to do in this collaboration is connect this way of thinking to the celestial world. There must be a connection, and there's even very concrete hints of a connection in two directions, one of them involving all plus amplitudes in pure Yang-Mills, which in the past few years, largely through the work of Johannes Hahn and his collaborators, all plus amplitudes at any loop order is conjectured, the leading transcendental part of all plus amplitudes at any loop order are captured by a quantity in N equals 4 super Yang-Mills that quite beautifully, that quantity also has a very simple and natural connection to the amplituhedron, is computed by the amplituhedron. So this is, I think, not widely appreciated, but there is a direct connection between the most complicated part, the most interesting part of all plus amplitudes at any loop order and N equals 4 super Yang-Mills and the amplituhedron on the one hand. And on the other hand, there's a picture for what the amplituhedron is directly in momentum space, or the space of the lambdas and lambda tildes for the scattering particles. It's called the momentum amplituhedron. And I felt that this should make some very direct connection with the celestial program. The variables that occur, the kinematic variables, are exactly the ZZ bars on the celestial sphere. But the difficulty was that this object did not have a, to me, supernatural definition. And it awaited a better definition, not just sort of uplifting what was known from the momentum twister standard amplituhedron picture. This picture changed dramatically back in November with a spectacular paper by the mathematician Pasha Galashan that gave an amazing ab initio definition of the momentum amplituhedron, directly in ZZ bar space. The paper is called The Amplituhedron in Origami. It's something I would never have come up with in a million years myself, but it's a remarkable, really remarkable thing. So anyway, I think the stage is set to actually do something. But we've had our hands so full just developing many aspects of this curves on surfaces story that I hadn't gotten around to doing it. So I was planning, I gave a couple of titles to come and talk about at least some of what I just said in a few minutes. But then I thought that's going to be pretty lame. I can't come to a celestial meeting, not say anything about the celestial sphere, and just say blah, 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 here's what I'm doing. So I thought at least I'd try to make it more special and take the opportunity of this coming meeting to go back to some of the questions that we thought we would try to make progress on in this business and try to make progress on them, just specifically for this meeting. So 2 weeks ago, we started. And so I'm going to report on work that's been going on over the past 2 weeks with Carolina, who's right there, and Giulio Salvatore and Hadley Frost. And it's actually not as bad as it seemed. We had some ideas for about a year or so already, but really stimulated by this meeting, by the coming of this meeting, we had sort of one key new idea that led to a lot of progress. And I want to tell you about that today. I'm very excited about these ideas. So it's Blackboard talk, because it doesn't deserve slides, and also because Blackboards are cooler. A word about the title. So when I was a graduate student, probably like many of you, I ran into Sidney Coleman's famous set of Eriche lectures on the large N expansion that were called 1 over capital N. And I thought, God damn it, that Sidney is so cool. How could you ever one-up Sidney Coleman? And I thought to myself, when I was a graduate student, there's only one way you could do it. If you wrote a paper 1 over lowercase n, I didn't know what that paper would possibly be. And so now I'm going to tell you about 1 over lowercase n. And of course, theoretical physicists have never run into an integer that they don't like to make large. Okay? And so that's what I'm going to talk about today. If you're thinking about scattering amplitudes, there's 2 obvious integers that you might want to make large. One of them is loop order. Okay, so let's go up in loop order. Here is sort of 0 loops, tree level, 1 loop, 2 loop, 3 loop. And the other integer, of course, is multiplicity, the number of particles, which is not to give it away, is now going to be the n of my talk. So maybe we start here at 3 particles, 4 particles, 5 particles. Okay?
You mean external particles?
External particles, the number of particles in the scattering process. Okay? Now, for obvious reasons, people care a lot about what happens up here. Okay? So what could happen if you go to very high loop order? That's presumably related to the strong coupling behavior of the theory. If you really understood what was going on at arbitrarily high loop order and really understood it, you probably understand something about strong coupling physics. I think it's fair to say that after 40 years, even in the planar limit, we don't have a super systematic way of thinking about strong coupling physics. Sometimes in some theories, vector, melonic, we find subsets of amplitudes that we can resum by some Schwinger-Dyson idea. That's one trick. If there are matrices in low enough dimensions, we switch to eigenvalues and Coulomb repulsion. That's another trick. We make guesses from ADS-CFT. That's another trick. But there isn't kind of a uniform picture for what strong coupling physics might look like. Okay, so obviously we care about large L. And you might also care about large N. Okay? It's also interesting, of course, it's another integer. So this is strong coupling. This is large multiplicity. But something I think many people in the amplitudes business know is that this and this are related to each other. Okay? The reason is that large loop orders somehow contain, large loops for a small number of particles contain the information of trees for a large number of particles in their cuts. Okay? If you cut loops, you open up 2 extra external particles. And roughly the complexity is on lines where 2L plus n is equal to a constant. Okay, so for example, a 3-point 1 loop amplitude and a 5-point tree amplitude are pretty much similar objects. Okay? The reason is that if you take a 1 loop diagram like this and you cut it open, you get a contribution to a 5-point tree. Okay? 2 loops, 7-point, and so on. Right? So large N and large L are not super disconnected from each other for this reason. Now, I think many of you know you're all professionals in the celestial business. Something that happens to you when you become a professional, I find, is that you're impressed more easily than before you were a professional. Okay, so as a professional amplitudes person, I'm super impressed with the recursion relations, BCFW, wow, it's all amazing. Before all this stuff, I'm like, big whoop. These recursion relations, they're all diagrams, one way or the other, right? They all look like you want to compute some higher order thing. You glue together lower point things. Some people call them Feynman diagrams. Some people call them on-shell diagrams. Some people call them BCFW terms. They're all basically the same thing, okay? And it's true that the way recursion relations work, even our best understanding of scattering amplitudes, kind of goes in this direction at tree level, right? You learn how to recycle the information about lower points to higher points. If you want to get the 1,000-point amplitude in any theory, nobody knows how to do it today, right? In any picture, it would break every computer on the planet if you tried to do it, with the exception of the famous formulas I'll come to in a second, that Tom is responsible here for. Also at loop level, this connection between multiplicity and cuts means that our information about loops goes in this direction. Okay, so you learn to compute amplitudes at high multiplicity like this, and then you can explore loop amplitudes by using cuts and going down in this direction. Okay, so what I'm going to talk to you about today is really something different. We're going to come up with a theory for what happens out here ab initio at infinite n. Okay, so there's going to be a real structure there, a real theory at large n. And my title's a little bit of a lie, because so far we've managed to figure out what the leading physics looks like at large n, and do not yet have a machinery for computing the 1/n corrections. Okay, but we think that we do have a picture for what's going on at large n, with all sorts of caveats, of course, that we will come to. No, you will see. I'll explain all of that. I'll explain all of that in a second. So just to be clear, what we're talking about, we're going to be talking about the trace phi cube theory. So this is the simplest theory of interacting colored scalars. It has this cubic interaction. As some of you may know, this looks like a super dumb theory. But over the past year and a half or so, we've understood that the super dumb theory actually contains in it interesting theories. The nonlinear sigma model, even non-supersymmetric gluons in any number of dimensions, are somehow contained if you understand the stringy amplitudes for this theory. Okay? That's theory that we're going to be talking about. And the large n is just the number of external particles. And I'll answer Hiroshi's question about what we hold fixed as we take n large. To actually tell you a little bit more, there's one more parameter here, which is alpha prime. We'll be talking about stringy amplitudes. And so I'm going to give you formulas for what happens both when alpha prime is close to 0, which is the field theory limit, and when alpha prime is very large, which is the sort of super high energy limit. Okay, so we're going to see simple behavior in these two limits. There's probably something simple in between, but we've been working on it for 2 weeks. Okay, so, all right. Now, before I say more, just some comparison with things that you may have heard of before. In the late 80s and early 90s, there was a spate of activity and actually confusion that I think has not been entirely resolved about these kinds of questions about what happens to scattering amplitudes when the number of particles becomes large. And this was for uncolored theories, the sort of simplest case, just ordinary phi cube, no color. And the issue was the number of Feynman diagrams grows factorially, and therefore the g to the n in perturbation theory is eventually overwhelmed by the n factorial. And so there was a question, are the amplitudes unsuppressed at super large multiplicity of order 1/g²? This is actually even a phenomenologically interesting question. If we ever build a 100 TeV collider, if this effect was there, you would see unsuppressed, for example, baryon number violation from processes at these high energy scales. Now, one way to approach this problem is to choose a super special set of kinematics. I think there was a paper by Voloshin, perhaps, which did this, where you specialize to n scattering, let's say, but where all the particles are exactly on threshold. See, if all the particles, so they're really just at rest, and they just convert from the first set to the next set. The reason that simplifies the problem, so you might say, look, large n is classical physics, so we should be able to solve this problem by solving the classical equations of motion. Good luck, it's a very nonlinear theory. It's not easier than summing the Feynman diagrams. But there are kinematic configurations which simplify, and if you're exactly on threshold, that's one of them, because everything only depends on time. All the dependence on space goes away. If everything depends on time, you can solve that classical problem easily. Because that's what Voloshin did, and anyway, there's lots of interesting things to move away from that limit and so on, but that's one limit which is solvable. All right, now other famous examples are, of course, the Park-Taylor formula. So we do have examples where we know the answer to all n. Okay, so Park-Taylor is a good example. When we move away, for example, if we talk about NMHV amplitudes or tree amplitudes for gluons in general, but for NMHV amplitudes, they're related to volumes of the corresponding amplituhedron. And there too, if you make, I won't talk about this at all, Akshay, who's in the audience, worked on this as a student and never wrote a paper on it, shame on you, right? It's very interesting. That if you make the external kinematics smooth in the large n limit, we'll talk about that point again, then you can think about the amplitude as literally the volume of a region that's sort of bounded by these guys, and it goes to a limit. Okay, so Park-Taylor is a beautiful formula. In the cases where we have a clean volume interpretation coming from the amplituhedron, we have some beautiful formulae for a continual limit. But I would say these are examples where going to large n is not helping. You have a beautiful formula already, then you can compute it, go to large n, and see what happens. Okay? Also, there are very special helicity configurations. There's not the generic helicity configuration. Right? What I'm going to be talking about today is just scalars, colored scalars, and generic momentum configurations. In the sense they're not special, they're not in one dimension, they're not in some super special configuration. They will be in certain positive regions. And again, the hope is there are some regions, as you'll see, there are some shockingly simple formulas that actually look very similar to the Park-Taylor formula in some cases that emerge in this limit. But the point is that the simplicity emerges in the large n limit. Okay, it's not there in general, and as you go to large n, things become simple. One reason, yes. The number of exactly. The number of colors is infinite. We're looking at a particular color ordering, and then we're sending the number of particles to infinity. So that's, I think, the really key thing is that the simplicity is seen at large n. And as you'll see, there is some kind of semi-classical theory at large n that involves random walks on the space of curves on surfaces. Okay, so there's an interesting semi-classical theory at large n, which we're learning to understand and perturb around. Okay, I'll give you examples of the formulas in a second, but let me first just talk about the theory and the kinematics so we know exactly what we're talking about. Okay. That's just what I'm coming to. Yeah, so the color in this entire story of curves on surfaces at the moment is very, very important. Okay, yes, absolutely. All right, so we're talking about trace phi cube theory. Again, so we just have this basic interaction, or you can fatten it to a fact graph. We're talking about color ordered amplitudes. So that means that, oh, sorry. And today I'm going to talk about tree level. It should be clear that a small number of loops, small relative to n, should not change the story much. Okay, so this is not about understanding classical physics, it's about understanding something else, as you'll see. All right, so we're talking about color ordered amplitudes. So for example, at 4 points, that means that everything is just ordered. So I'd have the S and T channel diagrams like this. There is a kind of I hope by now, standard picture where we can think about the kinematics. Because the particles are ordered, we can draw the momenta end to end on a d-dimensional piece of paper to get a closed polygon. And this picture of the polygon is very useful. The naive kinematic invariants are Mandelstams, things like pi.pj. But the pi.pj are constrained by momentum conservation. Okay, they're not super beautiful objects for that reason. Okay, so of course you can break the cyclic symmetry of the problem by solving for all the momenta in terms of 1 and so on. But they're sort of annoying objects. Also, they're not the objects on which the amplitude really naturally directly depends. For example, the poles of the amplitude do not occur when some Mandelstam invariant goes to 0. The pole occurs when some planar propagator goes to 0. And the planar propagators here is like p1 plus p2 squared, or p2 plus p3 squared. In general, the planar propagators correspond to what we call these planar variables. Okay, so we call these things xij, where these are pi plus dot dot plus pj minus 1 squared. Okay, it's not going to matter whether we're massless or massive. I just won't keep adding m squared all the time. The nice thing about these xij is that notice that momentum conservation is now just a trivial statement that xij is the same as xji. Okay, so it only depends on the chord and not some orientation of the chord. And another nice thing about them is that there is exactly as many xij as there are independent Mandelstams. So these are a nice basis for all the Mandelstam invariants. Okay, so that's why they're maximally useful. They're the physical variables that show up in poles, and they're a basis for all possible Mandelstam invariants. In this language, an amplitude is a very nice interpretation. For example, a 4-point amplitude, I just draw this foregone, and I triangulate it. Okay, so that's one triangulation. Here's another triangulation. The triangulation is dual to a Feynman diagram. I hope these are by now very standard things. Okay, so these are the S and the T channel diagrams. You can think either about summing diagrams or about summing triangulations of the n-gon. And the triangulations of the n-gon picture is especially nice because all you do is take your favorite triangulation and multiply the product of the 1 over x's that you see. So in this case, at 6 points, this would correspond to one diagram, and the contribution of this diagram would be 1 over x13, 1 over x36, 1 over x46. Okay? And then you just sum over all triangulations. Okay? So that's what the amplitude is, the summing over all triangulations. All right, so we've now defined what the field theory amplitudes are. I'll talk about the string amplitudes are in a second when we get to the stringy statements. But now let's talk about what the large n limit should be. Obviously, if you want to go to large n, something has to be smooth on the large n limit, right? Something has to be fixed. Of course, this gives a very natural picture for what should be smooth. We should just smooth out that momentum polygon. So the idea is that we want to make n large. We want to make n large. So this is the first idea, and I'll say it even more generally in a second. But imagine that you pick some sort of fixed smooth curve, and then you make n large just by sampling momenta off that fixed smooth curve. Okay? And the hope is that as n goes to infinity, the answer will only depend on the curve and not the particular distribution of points on the curve or anything like that. Right? It'll just be some smooth function of the actual curve itself. Now let me tell you another way of thinking about this, even more general way. What we've come to love doing in the past many years is thinking about the kinematic space. I want to stress this is just a picture, a child's picture. There's nothing deep about it. This is not a Penrose diagram. It's just a child's picture for keeping track of the variables, keeping track of the xij variables. Okay? But there's a way of keeping track of all the xij variables in what we call a kinematic spacetime. Do not confuse this with any real spacetime. Okay? This is what we call the kinematic spacetime, or let me call it the kinematic mesh, just to make it clear. But this is the way we think about it. For example, at 8 points, I draw a picture like this. Okay, so this is just recording index space, right? So 1, 3, 1, 4, 1, 5, and in the obvious way. This would be 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, and so on. Okay, so we can fill in the rest of the space in the obvious way. Why I draw it tilted 45 degrees and so on, never mind. Okay, so, but you can see that if you just wanted to keep track of all of the indices, well, this is what you'd do. Maybe you'd start drawing it like a normal person, not tilted. But anyway, this is what you do. But you'll notice that if I take this picture, of course it's periodic, right? I could extend it infinitely. That's just the cyclic symmetry of my problem. But for example, the variable 1, 3 occurs here, and 3, 1 occurs up there somewhere. Okay, so the actual periodicity is twice what you'd expect because you have 1, 3 here, 3, 1 there, 1, 3 again up there somewhere else. And so if you want out of this quote-unquote kinematic mesh to take out a chunk that just covers all the variables once and only once, you have to make a choice, right? So this is an especially nice choice to make. And you can see that every single variable in this region every point in this region, every ij in this region covers all of the xij once and with no repetitions. It's not God-given. You could choose many other sort of chunks out of this mesh that do the same thing. For reasons I don't have time to explain, this choice of chunks out of the mesh is in one-to-one correspondence with choosing some base triangulation. Okay, there's some sort of base triangulation of your surface. At tree level, there isn't much to talk about, because the surfaces are just disks. But in any case, to even define a surface, you have to give some triangulation that defines it. And so this picture goes along with a particular choice, a very particularly simple, what we call ray-like triangulations. And what you can see here is that the sort of variables on the quote-unquote past boundary of this little picture of Minkowski's space, okay? The variables on this little past boundary are exactly the chords in this triangulation, 1, 3, 1, 4, 1, 5, 1, 6. Okay, so this is not important right now. I might say something about it at the very end. All right, so in this picture, again, I can think about the variables as just the x's that I see here, okay? Now, remember I told you that the x's are a basis for all Mandelstam invariants, so I might as well give you a formula that tells you how to solve for the standard Mandelstam invariant. There's a very pretty formula that says minus 2pi dot pj is xij plus xi plus 1j plus 1 minus xij plus 1 minus xi plus 1j. Okay, so that's just a high school computation that tells you how to represent any old Mandelstam invariant in terms of these x's. And that has a very nice interpretation in this picture. You see, these combinations in this picture are exactly what you sort of associate with these little meshes. See, this is like x25 plus x36 minus x26 minus x35. Okay, these are exactly the combinations that show up in these pictures. So the kind of meshes in these, the little squares in these kinematic meshes can be naturally associated with the Mandelstam invariants in this way. Yes, there was a question.
Yeah. So if I give a different triangulation,
yes.
that corresponds different the path in the kinetic mesh?
That's right, that's right. There's a different chunk in the kinematic mesh picture. They all have the feature that all the xij's occur there once and only once. And there's a one-to-one correspondence between every triangulation and a picture like this that you can draw. Okay. All right. All right, so in this picture now, we can be a little bit more specific about what the large N limit means. Okay, because what we're going to do, and so we can either think about the variables as the x's. Sometimes it's useful, as you'll see in our setting, it's useful to think about the variables as the x's on the boundary, in this case, together with the c's in the interior. Right? That's another way. This way actually has a nice sort of physical interpretation. Solving for an x inside here is like solving the wave equation. It's like solving the discrete version of the wave equation with the x's here as the boundary condition and the c's as the source term in the wave equation. So this x here is given by Gauss's law by the formula that this plus this minus that is the sum of all the meshes inside, right? So this is, yes, and large limit will become the wave equation. Now, so this is another way to think about the kinematics, either as x's or in this way. And I'll go back and forth between them. Well, you wait till the end and we'll see. All right, so to take large N then, the idea is that we want to take n to infinity, but in such a way that xij is smooth on this mesh. In other words, you want to think that there's some function of some u and v, which are sort of the obvious coordinates here, but that xij would be, for instance, x of u equals I over n, and v equals j over n, picked from some smooth function x. Right, so we want to take the large N limit with sort of asymptoting to something smooth that we're discretizing in this picture. Okay, so that's what we want to do, and the claim is that when we're in a particular region, so first of all, we're going to be in the region where all the x's are so positivity is very important in our subject, okay? We have to be in a region where all the x's are positive. On top of that, in a region where the c's are positive. And on top of that, there's going to be some chunks of this positive space that there are going to be chambers in this positive space. As you'll see, the answer will have jumps as we go from one chamber to another as we go to large N. So it's not true for all kinematics. We're not giving random formulas that are valid everywhere, but nor do they involve their top dimensional volumes in kinematic space. Okay, that we're going to be talking about. Yes, Edward. In any fixed number of dimensions, they're not. So here we're imagining things that are true also in infinitely many dimensions. So it's a question that we don't know the answer to yet, whether the chunks that we're talking about are exactly how to realize them in terms of momenta. We have not thought about that yet. If you're in a fixed number of dimensions, the pi.pj's satisfy the Graham determinant conditions. And you can, of course, translate those into xij. So there's some sort of polynomial equations the xij's have to satisfy if you live in 4 dimensions, 5 dimensions, any fixed number of dimensions. Here we're imagining that those conditions are not there. Of course, the amplitude itself doesn't know anything about those conditions. The amplitude itself is defined in any number of dimensions. All right, so. Yes. Yes. Probably, but it's not, I don't have anything to say about the question of whether there's a conflict between fixed dimensionality and what we're talking about. OK, so.
You didn't define what CIJ is.
Sorry? Oh, I'm sorry. The CIJ are just exactly these. The CIJ are exactly the minus 2pi.pj. I'm sorry. We just call them CIJ for historical reasons, and that's exactly these meshes. Sorry about that. Thanks, Guy. OK. Now, let's do a little warm-up just to see what to expect. And the warm-up is also an excuse to tell you how to actually, how you can brute force compute the amplitudes using recursion relations. So this is going to be our ground truth we can eventually compare to.
These particles are all identical.
They're all identical, but they're colored. Sorry?
It's translationally invariant.
It's cyclically invariant around the circle, yes. The choice of this chunk of the mesh breaks cyclic symmetry. Okay, so that's part of the, it's true. The amplitudes, of course, don't depend on the choice you make, but the sort of pictures do. The regions in the kinematic space I'll be talking about where something simple happens definitely break that symmetry. Okay, so so for different choices of this triangulation, you'll get different regions where you can predict something simple. Okay, so just to be clear, we're not predicting there's one formula valid everywhere. Instead, we're finding that there are places in kinematic space where the answer simplifies dramatically to sort of one-term formulas. But the one-term formula jumps from chunk to chunk to chunk. And it's a very interesting question to learn how to glue all these chunks together. But this will become clear when I say it a little less abstractly in a second. All right, let's do a warm-up. A warm-up is to see what happens. So the smoothest that the x's could be, they could all be equal. Say all the xij are equal. So that means that every diagram has n minus 3 propagators. Every diagram just gives you 1 over x to the n minus 3. And so the amplitude is just equal to the number of diagrams. So 1 over x to the n minus 3 times the number of diagrams. Now, there's a very famous and sort of high school way to calculate the number of diagrams given by Catalan numbers. And it's the observation that if you want to sum over all the triangulations, there's an obvious recursive way of doing it. The obvious recursive way of doing it is to imagine you have a big polygon. You have, you're summing over all triangulations. That means, in particular, the edge n1 has to be in somebody's triangle, some triangle somewhere. So choose a j here. Okay, so in any triangulation, the edge n1 will be in some triangle, in the triangle n1j. And then the entire rest of the triangulation has to triangulate this side and triangulate that side. So that gives you a recursive formula for the amplitude. The amplitude is equal to this 1 over x times that 1 over x for these two propagators times the amplitude on this side, which is the sum of all the triangulations, times the amplitude on that side, which is the sum of all the triangulations. Okay? So that very simple thing in physics is called the Behrens-Schiele recursion relation. In math, it's called Euler. Okay? One of a million things Euler did. And so in particular, if you do the case where all the x's are equal, there's a very simple recursion relation. If Cn is the number of diagrams for n points. I'm not going to be precise about little offsets, but a formula like this tells you that Cn is a sum over k of Cn minus k times Ck. Okay, so this is a famous Catalan recursion relation. If you make a generating function for all these numbers, which would start as 1 plus x plus 2x, that's the sort of 2 point, 3 point, there's 1. 4 point, there's 2 triangulations, the S&T channel. 5 points, there's 5. 6 points, there's 14, and so on. Okay, then it's very simple to see that this recursion relation implies that C satisfies that C of x is equal to C squared of x plus x. So this is, again, one of the dumb, direct ways of summing the diagrams, right? In this case, we can do it and solve for C. And C of x is very famous formula, 1 minus root 1 minus 4x over 2x. Okay? That root 1 minus 4x might remind you of the Wigner semicircle formula. It's not at all a coincidence. It's how the Wigner derived the semicircle formula by doing precisely this kind of counting. He didn't know about path integrals and eigenvalues and Coulomb repulsion and all of that stuff. He actually did this, the analog of this summation. But for our purposes, the important point here is to notice there's a branch cut at x equals a quarter in the x-plane. Okay? There's a branch cut at x equals a quarter, and that means that the number of diagrams must grow as 4 to the n in order to give us a breakdown of the expansion at x equals a quarter. So that's the sort of fastest way of seeing that the number of diagrams at tree level grows like 4 to the n. Right? Oh, yeah. Well, yeah, I mean, it's not even that. Again, if you want me to draw a picture of the momentum polygon that does it, I can draw it for you later. But this. No. This does not depend on the triangulation. All the x's. This is all the x's, all of them, not just these ones. All of them. All the x's equal. We've just made all the propagators the same so that we're just counting diagrams. But already in this case, we get a nice formula, right? Already in this case, if all the x's are equal, we see that the amplitude at large n goes like 4 over x to the n. That 4 is meaningful. Right? I've suppressed the coupling constant, so it would be some 4g over x to the n, but I'm putting g to 1. So the amplitude goes like 4 over x to the n. So we see maybe now what to expect. If I take the log of the amplitude divided by n, this goes to something nice at large n. It goes to log 4 over x. Right? So that's our idea. That at large n, the amplitude goes like e to the n times something simple. 1 over n looks like a coupling constant. The something simple in the exponential is something that we're now going to learn to compute and to come up with a 1 over n expansion for. Okay? But do that not just in this dumb case where we can count them because Euler counted them, but for much more generic kinematics. All right? Now, since I don't want to keep writing down log a n over n, I'm going to just have a notation for the rest of the talk that I'll say that a goes to b if log b plus order 1 over n to a power, if log a over n goes to log b over n plus order 1 over n to the power as n goes to infinity. Okay? Okay, so I'm going to be telling you a lot of b's in this talk now, right? All right. Before we move on, telling you what the answer looks like, let me tell you what it looks like. This is at large n in the field theory limit. Let me tell you what it looks like at large n in the super stringy limit, okay, when the x's are huge. The analog of this computation, but where the x's are enormous compared to alpha prime. Okay? Well, first let me tell you what we're talking about, what's sometimes called the stringy par-Taylor formula or Z theory. It has different names. It's basically the bosonic string amplitude for tachyons, but with a kinematic shift so that the tachyons have 0 mass rather than mass squared equals -1. This has been an object that we've been learning to think about in very different ways, but let me first just remind you the standard formula. The standard formula, now at finite alpha prime, is there's some amplitude that now depends on alpha prime. It's alpha prime to the n minus 3. It's an integral dnz mod SL2. And then there's this world sheet par-Taylor factor. And then I have the Kobe-Nielsen factor, the product of Zij to the 2 pi dot pj. alpha prime. Maybe there's a minus sign, I don't remember. Okay, so this is the object that we're talking about. Now, it'll become maybe a little obvious in a little bit why we can do this, but when all the x's are equal, and x is much, but alpha prime x is much, much bigger than 1, then we can also solve at all n for what this amplitude looks like. This is something that we did in a paper with Carolina and Grant Remen, just incidentally, back in the fall. Let me just quickly say the reason we can do it. In this limit, of course, in this limit, the amplitudes are governed by solutions of the scattering equations, the Gross-Mende equations. And in this limit, where all the x's are positive and large, it's really easy to find these saddle points. It's really easy to also find the saddle point that dominates. And it actually has a very simple geometric interpretation. It's when all the z's, the points on the world sheet, are just uniformly distributed around the disk. Okay? So because of that, it's very simple to solve. And the formula for any n at large x is that an is equal to 1 over 2 cosine pi over n to the power of nx alpha prime, when alpha prime x is huge. Right? It's a very beautiful formula. And as n goes to infinity, it also simplifies. It's a half to the nx. You can remember that. Okay? But you see, once again, it's exactly the same structure. It's the exponential of n times something. Right? So the super stringy amplitude, log of the amplitude over n, now goes to x log a half. Okay? All right, and so we would say by my same notation that the super stringy amplitude, the amplitude in the very stringy limit, arrow goes just a half to the nx. Okay? So in the cases where all the x's are equal, in the case where all the x's are equal, we have two n's. Counting diagrams, it goes like 4 over x to the n. Opposite limit, super duper stringy, goes like a half to the nx. Right? And so now we'd like to generalize away from that. And now, having told you what the variables are, let me just tell you what the answer turns out to be. And then I'll try, in the time I have left, to explain where it comes from. Any questions so far? Sorry? What was the question?
Catalan limit of the usual Park-Taylor formula for
Yes.
Yang-Mills.
Yes.
What does that look like?
Product 1 over II plus 1?
Same.
Yes, you should ask him and not me, yes. Yeah, so that's what I was saying earlier. Park-Taylor and even its close cousins, like the NMHV amplitudes, are also examples where we know the answer at all n. But first, it's very special amplitudes close to the self-dual limit. Secondly, it's what I said, they're already simple. At finite n, they're already simple. They're not getting simple at large n. The novelty here is that we're not talking about any special helicity configuration, they're just scalars. We're going to be in generic momenta, although some positive regions, but not like in one dimension or some special collinear limits or anything like that. But large n smooths out the answer. That's the exciting thing, that there's a specific sense in which summing over all the diagrams, the nearby diagrams are not so different from each other, and there's a sort of a semi-classical limit of the whole integral. Okay? And that's exactly what's handed to us on a plate by this way of thinking about amplitudes in terms of curves on surfaces. So that's what I'm going to try to explain. And in fact, we said in our paper from a year and a half ago that this was one of the potential killer apps of this idea. The whole point is that we find a way to represent the amplitudes, a whole amplitude, not just a tree level, loop integrated. The whole shebang is an integral over one simple giant space. And that somehow large n should maybe smooth out in some way, and there should be some theory around large n. That was an idea that we had already a year and a half or 2 years ago, and 2 weeks ago, we started taking it seriously again and started making progress. That's what I'm telling you about. Yes, Kevin? Yes, I mean, somehow it is like that. Tree amplitudes at any n can be thought of as not solving the full classical equation. I mean, if you want to compute tree amplitudes, what are tree amplitudes computing? Like if you have an n-point amplitude, it's like you take n-1 incoming waves, and you want to know what waves come out. But the full amplitude, the full classical solution is like is like the form factor with one leg off shell. The amplitude is just the part of the classical solution that has a wave coming out at infinity. So that's what we're doing. Just at tree level, that's just what we're doing. It's just that saying that doesn't make it especially easier. Okay? It does if you go to these simple limits like being on threshold where the problem becomes effectively one-dimensional. But we're not doing that. Okay? The problem is not effectively one-dimensional. All right, so let's go back to this picture. Let me just tell you what the answer ends up being. And I'm sort of deliberately telling it to you in this way so you're more surprised. Because when you see it from the surface picture, it'll be a little bit less surprising. But let's just look at this for a second. So remember, these were the boundary x's. I'm going to think about it in this language. And in principle, the answer depends on all the x's inside here, or these x's and all the c's, right? It depends on everything. The claim is that at large n, remarkably, the answer decouples, the interior points entirely decouple. The answer is entirely fixed by the knowledge of those meshes. Okay? And furthermore, let me tell you what the answer looks like. So just so I don't write slightly complicated formula, I'm going to make some notation. Let me just define AK to be the variable x1k. Bk is the variable ck minus 2k. So these ck minus 2k's are exactly these meshes, 1, 3, 2, 4, 3, 5, and so on. Okay, so these c's are these meshes, ck minus 2k minus x1k. And then this corner guy, c1 n minus 1, I'm going to call it c star. That plays an interesting role in the story. Okay, so here are the formulas. So, and I'm going to give it to you in a few kinematic regimes, and we're trying to understand more of them. But here are some very simple regimes. For example, if all the AK are smaller than BK, then the amplitude asymptotes to this shocking formula, just sum of 1 over AK plus 1 over BK. Okay. That's it. Plus order 1 over n. If, here's another regime, if AK is bigger than BK, now it depends a little bit on C star and a few other things. So if AK is bigger than BK, but also AK minus BK is non-decreasing with K. See, all these things seem crazy now, but they'll be very obvious from the curves on surfaces picture. So this AK minus BK has to be non-decreasing with K, and C star should be, for example, big compared to the biggest of these guys, over 2. A minus B over 2. In this limit, the amplitude goes to something, if anything, even slightly simpler, the product over K, 4 over CK minus 2K. That's it. Plus order 1 over square root of n. And that square root of n should be the sign that we're going to be talking about random walks. Okay, so the semi-classical theory controlling this at large n is going to involve a picture of random walks. All right, I should say that the case where all the x's are 1 is this one, corresponds to this one. You can sort of very easily see that that's a case where all of these are equal to 1. It's non-decreasing. C star is equal to 1. So all these things are saturated. And this is the product of 4 over x. That's exactly our Catalan counting. Okay? This is a different case. Okay? This is not covered by that. And there's all sorts of things in between. Okay? There's all sorts of, but these are sort of 2 simple chunks of kinematic space where we run into these very simple formulas. Yes?
So there's also a way to take the model to be large to reach the classical theory.
This should be classical field theory.
Does it overlap with this?
It absolutely should. It's not an easy to solve even classical field theory. What we're solving is the problem of a bunch of incoming waves and what the outgoing wave is.
So is there
right?
a way to see that these answers related to your factorization?
I don't know. No, that's exactly what I was saying. I mean, the sort of closest that's been done is this Voloshin picture for the uncolored phi cube theory that I know of, where when the particles are on threshold, you can, and so the physics becomes independent of space, only dependent on time. You can relate the calculation of the sum of refinement diagrams to solving a very simple classical set of equations. But we're not in that limit. There's nothing simple about the kinematics here. Okay, we're in sort of regions of kinematic space, but there's nothing especially simple about the kinematics. And as you'll see, it has very little to do per se with classical physics. As you'll see how I mentioned that it's very likely that the picture continues to hold, even including loop correction, so long as the loops are small compared to n. You'll see in maybe the 10 minutes I have left what the idea is. Yes, Edward.
Because the particles are color ordered,
Yes.
it's not clear to me if large n corresponds to a classical field.
Indeed. Indeed.
Loops, you might as well get a string theory.
Yes, indeed. Indeed, of course. Yes, yes. Yes, yes. Indeed. Yes. Yes, indeed. Yes. It's just, but you might think it corresponds to solving classical equations. To just at fixed n, it does. This is solving some the outgoing wave for a bunch of incoming waves, solving that classical problem. But I agree with what you said.
Are there factors a little n in going from the color ordered amplitudes to actually?
No. No. Well, it's just a particular color ordering. So there's something interesting that happens when you sum over color orderings, dress each one of these partial amplitudes with a big trace. That's a very interesting question. I don't know what that does. This is specifically for a given color ordering. But but what the real point I want you to see in the 10 minutes I have left is a sense in which summing over all the diagrams smooths out. Okay, that's really what I want you to see, and what kind of semi-classical physics is controlling that. Yes. No, and all the x's are the same. Not all these c's precisely are not 0. In fact, I'm going to come to this, so let me make this point now. You see, imagine we go to the continuum limit, okay? Or n is very big. Look at these c's on the inside. They look like x plus x minus x minus x. That looks like a double derivative, right? So that is something of order 1 over n squared when n is large. So you see, if for some reason you knew ahead of time the c's matter, then you say, oh, well, the c's inside are very small. The c's inside are going like 1 over n squared. Now, that doesn't mean that they're irrelevant, because there's order n squared of them. So there's lots and lots of c's that are very, very small. But nonetheless, the c's on the inside definitely seem, they're small. Precisely these boundary c's are big, because they're x plus x minus 0. Okay, so these guys are all of order 1, and the guys in the bulk are of order 1 over n squared. Okay? And so that's so somehow you're seeing that the semi-classical physics is determined by this boundary stuff, and the interior does not matter at all. Okay? Now, I should say before going on at all is that from what I told you before, that recursion relations, the physicists call the Baron-Schiller recursion relation, you can, for these simple scalar theories, you can run it on your laptop up to n of around 200. Okay, so all these formulas are checked for n of up to 200. Right, so they're all correct. And yes?
So for the channels that seem to be missing from the
yes.
You can't
we can't access them because of this. Exactly. That's right. So the Cliff asks, how can these formulas be correct? Because they don't even have the right poles. Right? This formula, I mean, you expect to have poles in the x's. This formula is just 1 over c's in it. Well, the regime in which it's valid is where you cannot access any of those poles. So that's somehow maybe another way of saying what's going on is that to those of you who know a little bit about what's going on in this business, is you see this looks like some insane factorization of the amplitude. Right? You go to large n, the amplitude just crazily factorizes into the product of incredibly tiny, essentially 4-point factors. That's a phenomenon we've been seeing all over the place in the surface world. Factorization away from poles. It's totally unobvious from Lagrangians. It's totally obvious from the surface picture. And this is another avatar of it, now at large n, super generically. Okay?
For the case
yes.
of constant x,
yes.
Case,
yes.
I would have thought that this x scans would hit the stringy residues.
Yes.
Can you see the?
No, this is the opposite limit. The stringy limits here would be when x is negative. Here we're going to x is positive. The regime where the amplitude is manifestly exponentially small. Yeah. No. It really looks like a half to the x. It's just super exponentially small. No. It's if you tried to continue it to small x, you would get the answer you're looking for. But that's right. This formula is valid when x is huge. Exactly. Okay. So all right. So what can I? Oh, sorry. But let me at least tell you what the formula is in the super stringy limit.
Quick question.
Yes.
The second case, is that convolution or addition?
Sorry?
The AEK minus
No, these are the conditions. These are the conditions that have to be satisfied for this to be the correct formula.
But what
Okay?
about the second instance
we have some formula for various intermediate cases as well. We don't have a complete picture yet. We would love to have a formula everywhere in kinematic space. We're very, very far from having a formula everywhere in kinematic space. Okay? All right, but just to give you what the answers look like, well, let me just give you one of them. For example, just this one. In fact, the arguments are much simpler, are less subtle in the very stringy limit than in the field theory limit. Let me just give you the analog of that one. So when alpha prime x is very big, this just goes to exactly the product over k, a half to the ck minus 2k, for example. In the same condition here, this is what the amplitude goes to. Okay, so once again, when all the c's are equal and equal to x, this goes back to the half to the nx formula. And there's anyway, I'll just write down, it's a trivial formula also for this case. Because I have 5 minutes, I don't want to write it down. All right, so I have 5 minutes, so how I'm going to do this. Let me try to, all right, I'll give you an idea of how it works. Okay, our starting point is this picture of amplitudes, where the stars of the show are curves on surfaces at tree level. This is literally going to be just a way of rewriting the standard Park-Taylor string formula I wrote down. So we have the string amps in terms of curves on a disk in this case. And again, the normal amplitude is like this integral dnz over the Park-Taylor factor, the Kobe-Nielsen factor. And the defect of this formula, I mean, it's a perfectly correct formula. It's physically related to the world sheet. And you see where it comes from. It comes from a picture of vertex operators inserted on the world sheet, and their correlators give you that factor. So the momenta are directly the kinematic variables the amplitude depends on. What's bad about this formula is that the singularities are not obvious. Okay, for example, we know the singularities in the field theory limit correspond to planar propagators. As I said, that's not obvious in this formula. Okay? And anyone who's ever done these computations, you fix a gauge, and some of the singularities are obvious in that gauge, some of them aren't. In general, you have to blow up. You have to do manual blow-ups of the integration, of the integrand and the integration domain in order to identify what all the singularities are. Those manual blow-ups are trivial at 4, you don't have to do them at 4 points. They're basically trivial at 5 points. They get manually harder and harder as you go to higher and higher points. The entire point of this curves on surfaces formalism is, from this point of view, to solve this problem. All the singularities are blown up, and the variables that you see are the variables the amplitude really depends on and has singularities in. So instead, we write this formula as the integral of a simple form. I'll be very explicit in a second. But for every curve on the surface, we have one of these things we call u variables. For every ij, there's a uij. Its exponent is xij. Right? And these u's have many beautiful properties I don't have time to review here. But the most important thing is that all the singularities occur when a uij goes to 0. And when a given uij goes to 0, the ukl for all chords that cross ij go to 1. Okay, they have this remarkable binary property. And this means that this factor just beautifully flat out factorizes when a given, if you go in the neighborhood of when some uij goes to 0, what you're forced to go to when the corresponding xij goes to 0, because all of the KLs that cross it go to 1, they drop out of that product, and you just get flat out the product of the left and the right. So factorization is just trivial in this picture. Okay? Now, more than that, so Kobe and Nielsen, in fact, it's a wonderful historical fact, that Kobe and Nielsen, before this formula, wrote down that formula. Okay? And the reason they did it precisely was that it made factorization much easier to understand. it was quickly abandoned in the favor of this picture, A, because this was related to a physical picture ultimately of even before the worldsheet, some simple picture of a Coulomb problem in 2 dimensions, later turned into a worldsheet. B, you could then port it to loop order. No one knew how to extend these things to loop order. The central thing that we've learned how to do in the past few years is solve this problem. Now we know what these variables are and how to make sense of them at all loop order. So there's a picture for which the variables are correct, they're about the correct singularities, and furthermore, you can, and this is the final point, all the blowups are done for you. All the blowups are done for you, not just by abstractly writing these things down, but by writing these uij's as a function of some other variables that we call positive variables, u. These are ratios of some polynomials in these y's. The integration is n-3 dimensional. We have n-3 y's. So these are simple ratios of polynomials made out of these variables. And this form is just the product of all the dy over y's. So this is a simple d-log form. All of its singularities are where y goes to 0 or infinity. And this blows up all of the singularities. So there's no manual blowups to do. All the singularities are just in your face. That's the central thing that makes it trivial to take the field theory limit, for example. Okay, so you can trivially take the field theory limit of these expressions and have something. I'll give you an example in a moment. Oops, I'm out of time. Can I have, not this is maybe entirely shocking, but can I have, who's the boss? Who's the boss? You're the boss. Greg's the boss. Oh, Greg owes me a few things that, a few small things. I have the receipts that, okay. I wish I could have used it on something better, but. All right, okay, I'll just take, if it's okay, just 5 more minutes in my frame. Okay, okay, so, yeah, so let me say how this, so let me say how this works concretely. So, so for example, at n equals 5 points, this way of writing the 5-point amplitude is A5 is alpha prime squared, that doesn't matter. But I have, so first of all, you have to choose, as I mentioned, a base triangulation, or equivalently a base diagram to define your surface. Okay, so this is my base triangulation and my base diagram. And with every sort of chord of the triangulation or every internal propagator, there's one of these y variables. So here there's a variable y13 and a variable y14, for example. So the integral is integral dy13 over y13, dy14 over y14. And that general formula that I wrote down, when you write all the u's out, everything in terms of polynomials, I could spend a lot more time, but just so you see what the final answer looks like, it looks like y13, let me put alpha prime to 1 to the x13, y14 to the x14. And then we have these 3 interesting factors, 1 plus y13 to the minus c13, 1 plus y14 to the minus c24, and then finally, 1 plus y14 plus y14, y13 to the minus c14. All right, so this is what the amplitude looks like. Now, why is this interesting? Well, all the singularities here, see they're all only plus signs in these polynomials. You need the x's to be positive for this integral to converge. The y's go from 0 to infinity. You need these c's to be sufficiently positive for the integral to converge as the y's go to plus infinity. Okay, and so you see, but it's convergent everywhere else. So all the singularities of this guy come from y either going to 0 or infinity, right? So we can rewrite, let me rewrite y13 equals e to the minus t3. I won't put the 1 here just to save myself the time. y14 equals e to the minus t4. Okay, and therefore y goes to 0 or infinity in all possible ways is just going to infinity in t space. Right, so here this is t3, t4 space. And it's just going to infinity in t3, t4 space in every possible way. And now you see what happens. If you go to infinity in a random direction, well, these are complicated not that complicated, but a little bit complicated polynomials. But as you go to infinity, some monomial in those polynomials is going to dominate, right? So the singularities which are coming from this region as you go to infinity are entirely controlled not by the complicated polynomials, but by figuring out which monomial dominates in them. This is a sort of a grade 10 thing that you can call tropical geometry if you want to. Okay, tropical geometry is a little bit more than this, but surprisingly not that much more. Okay? So for example, what is 1 plus y13? 1 plus y13 as t goes to infinity, whatever it is going to be e to the power of the max of 0 and minus t3. Whichever is bigger, right? That's going to be the thing which dominates. 1 plus y14. Shoot. 1 plus y14 is going to be, as t goes to infinity, e to the max of 0 and minus t4. And this more complicated polynomial, 1 plus y14 plus y14, y13 is going to be e to the max of 0 minus t4 minus t4 minus t3. So the whole amplitude, as alpha prime goes to 0, the field theory limit, we can just take without thinking. All we do is we replace those polynomials by these, right? And so as alpha prime goes to 0, the amplitude goes to an integral dt3, dt4, e to the minus some action, where what is this action? S is t3 x13 plus t4 x14. This came from the y13 to the x13, y14 to the x14. That was the easy part. But then I have plus c13 max of 0 and minus t13 plus c14 max of 0 and minus t4. And then the c24, and then the interesting term plus c14 max of 0 minus t3 minus t3 minus t4. Okay, so in a sense, I could have just started with this formula. Forget about strings, blah, blah, blah. Just start with this formula. There's even ways to sort of directly land on this formula if you like. What have we done? We've somehow written the amplitude as a global Schwinger parameterization. Right? The integral over t space is summing over all the diagrams together. And you see what the magic is. You see here, these maxes in any particular region in t space, well, one of these t's is going to dominate, and these are going to be linear. Okay, so it's just an interesting question. You know, what are all the regions in t space where this guy's linear? It's a simple exercise. If you work out all the regions in t space where this guy's linear, you get something, you see a picture like this. The fascinating thing is that you get a picture where the t space is broken up into 5 cones. These are 5 regions where these expressions are piecewise linear. Furthermore, you can identify, I can fruitfully label these axes in this way. And for example, in this region in t space, this is t3 and t4. In this region in t space, that linear expression is linear in here. In here, this expression is the Schwinger parameterization for this Feynman diagram, 1, 2, 3, 4, 5. Okay? In here, it's a Schwinger parameterization for the diagram, and this is the diagram that has x13 and x14 in it. Here, it's a diagram that has x14 and x24, x24 and x25. Okay? We have automatically broken up the space into Feynman diagrams. We never said the word Feynman diagram. That's the interesting thing. The formula for the u's are given entirely by a question about a curve on the surface, purely about that curve. And there's a formula for it purely about that curve. It knows nothing about the other curves. It knows nothing about why the space should be divided up into diagrams. It automatically divides it up into diagrams. Furthermore, already in this tiny example, you see what's going on. There's 5 diagrams, but the 5 diagrams are being generated only by 3 interesting polynomials. There's fewer polynomials than diagrams. This example is very small, but as we go to larger n, it reflects the point. At large n, what's going on? At any n, the formula is the following. At any n, at any n, the full string amplitude would be this integral. The full amplitude would be this dy13 over y13 up to dy1n minus 1 or y1n minus 1. And then we have this product over these polynomials that I mentioned to the minus Cij. And these polynomials are very simple to read off from this mesh picture. Let me just show you what it is at 6 points since we did 5 points. So if you want to know the polynomial that goes along with C13, which is this mesh, it's 1 plus y13. What goes along with this mesh is 1 plus y14 plus y14 y13. From this mesh is 1 plus y15 plus y15 y14 plus y14. Anyway, you get the point, y13. And similarly up here is 1 plus y14. These guys here are simple, and they get slightly more complicated in the obvious way. 1 plus y15 plus y15 1 y4, and 1 plus y15 at the top here. Okay? I'm not telling you where these polynomials come from, but this is the whole story of this formalism, ultimately related to a very simple counting problem associated with the curves on the surface. Now, if we want to take the field theory limit, be my guest. This just turns to e to the minus s, where s is just equal to the sum of where we always put y1j as e to the minus tj, and s becomes the sum of tj x1j. It has a term which is c13 max of 0 and minus t3 plus c24 max of 0 and minus t4 and so on. And then it has a contribution from all the other c's. And let me highlight this most complicated one. The corner one is c1 n minus 1 max of all of them, 0 minus tn minus 1, minus tn minus 1, minus tn minus 2, and so on. And then, sorry, Greg, and then I have all the other c's. All right. Yeah, I know. Just I think 2 more minutes, and I think you will see the point. All right. Just so I say something. Now, the point is simply the following. If you look at this picture, there's an obvious thing to do. Why is so? Sorry. The point to make is that this is it. This is the whole expression. There's every one of these terms is a simple max of at most n things. There's order n squared terms for every sort of curve. But the remarkable thing is that this breaks the t space up into roughly 4 to the n regions. It produces all the diagrams for you. That's the point. But it also gives you a reason to expect things to become smooth in the large n limit. Because, these maxes, they're not changing that much as you move from place to place. There should be some sort of smoothing out as you go to large n. And in fact, the point is, at 0th order, and this is all I'll have time to explain, that you can fruitfully think of this s as s0 plus s1. You think of s as s0 plus s1. S0 is this part, the part where everyone is decoupled. S1 is everything else. Okay? S1 is everything else, where this guy is the star of everything else, and we can begin by forgetting everything else. One reason to forget everything else is the reason I told you before, that in this continuum limit, all the internal guys are of order 1 over n squared, but these are the big c's. Okay? So it's useful to start from this picture. And if you completely ignore this, you can just do the integral over the t's. They're entirely decoupled. What is this picture doing? In every t, this action looks like something linear, here and there. This has some slope ak and some slope bk, which are precisely, in tk, which are precisely the AKs and BKs that I talked about before. If you just do the integral over S0, ignoring everything else, you get literally the product over K, 1 over AK plus 1 over BK. And that tells us how to include everything else. We can interpret the full amplitude. The full amplitude can be thought of as our guess, this guess that I just said, multiplied and divided by exactly, well, just multiplied and divided by it, which I can think of as the expectation value of e to the minus s1 in a probability distribution given by s0. Okay, this is a probability distribution that goes like e to the minus t with some constant on one side or the other that you can think of as a biased random walk. Okay, you jump to one side and you jump to the other side. And now you can see why things like whether A or B are bigger matters. Okay, for example, if A is smaller than B, this is a biased random walk and you mostly want to jump in this direction. Because you're mostly jumping in this direction, the t's are mostly positive, and in these maxes, the 0 wins. So that's why you get one super simple formula in that limit. In the opposite limit, the jumps are going the other way. And what you have is a random walk where this bias to go in the other direction, but this C star, this term is a very big penalty. So it's like a random walk. Here are the T's. You're sort of random walking up and down. There's some bias that once it makes you go down, but there's a sort of wall of C here that wants to stop you. It's like a ping pong ball that's in wind and constantly banging into this wall. So what is it going to do? It's going to just random walk around there, but it's not going to drift up in general because the wind is down. It's just going to stay in the neighborhood of this wall forever. And that lets us find a sort of different background to expand around, where we can compute the answer and control the corrections to get the second set of formulas that I told you about with the root n. The physics is that of a biased random walk, drifting, and controlled by these semi-classes.